Again, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Welcome to the special lecture of the Introduction to Basic Probability by Dr. Muhammad Fariz Fadillah Mardianto. So, while waiting, there's some noise right now. So, I hope that the student and also the rest of the participants would switch off your mic. Please switch off your mic. Okay. So, before we start, I would like to briefly explain about our speaker today. Dr. Fariz is a lecturer in a study program of statistics, Department of Mathematics at University of Airlangga, Indonesia. He received a bachelor and master from Institute Teknologi of 10 November Surabaya and a PhD from Universitas Gadjah Mada, Yogyakarta. He has a wide experience and interest in statistics, where he is also a consultant for data analysis and become a member of professional bodies like Indonesian Mathematical Society, the National Statistic Institute, and Ikatan Perstatistikan Indonesia, and a few more. With that, we thank Dr. Fariz for the opportunity to have a special session with us. Hope that our student would be able to get more knowledge from you today. And with further ado, I invite Dr. Fariz for the lecture. And Dr. Fariz, the floor is yours.
Okay, thank you. Thank you. Thank you for UITM Malaysia Kedah. Ninayan. Thank you for Miss Shafiza Saila, our moderator, and other colleagues, Dr. Rosi Tona and Dr. Atira. Thank you for the opportunity. Okay, let me introduce Dr. Fadillah. I'm a lecturer and researcher in Universitas Airlangga, Surabaya in Indonesia, and I will share our presentation. Okay, is it clear for our slide? Clear?
Dr. Fariz, we can't see your slide yet.
I think connection problem. Okay, Dr. Fariz.
Okay, so while waiting for Dr. Fariz, maybe all students can switch on your camera.
Okay. Tambah. Okay. Okay. This is our profile. Okay, you can contact us in email in WhatsApp. In Universitas Airlangga, I teach probability course, and sometimes I teach probability course in other university and have visit in Malaysia. I have visit in Langkawi, attend UITM event, ICMS about in 2007 in Selangor, in Inti International University and in University Kebangsaan Malaysia, UKM, and then I have visit in University of Malaya and UTM. Okay. In this session, my student will accompany me will help me to share our ice breaking or our exercise in this task or in this lesson. So my student, there are two students, Naufar Ramadan Ahwat Siregar and Inkep Ika Dek Pasek Kusuma. Both of them have visit Malaysia, and this is our picture in front of KL Central Station in Kuala Lumpur. Okay, this is our documentation. I have some event in Malaysia, in University of Malaya, and then in Kuala Lumpur City. And this is our department office. Okay, in this session, we have 6 points or six subsections. And the first is about set theory as an introduction. And then the second, we learn about counting techniques, include combination and permutation. And then the third about probability measure. The fourth about some properties of the probability measure. The 5 is about conditional probability. And then the 6 about bias theorem. Okay, I have a motivation, the motivation from two statistical statistician person that very famous in the long ago. The first about probability is the most important concept in modern science, especially as nobody has the slightest notion what it means. So now this is modern science, big data science, and etc. So probability or statistical in a classical approach is still necessary. So probability concept is important to all of major, for business, for economics, for social science, health science, for IT, and etc. And then the second, we have quote from John Keynes. We use probability when we want to make an affirmation but are not quite sure. And all of aspects need probability as a consideration. Yeah. Okay. Jadi, so all of science need probability concept because life is probability. We do know tomorrow we still live in the world or pass away or etc. And yeah, okay. We don't know what is the risk for something, for to do something. What is the risk? How big the risk and etc. Okay. Okay. The first I will deliver about set theory as an introduction. What is set? Set is a collection of distinct sub-objects. A set is a collection of distinct objects or different objects. The objects in a set are called elements or members. Could you share the example of a set, like a set of fruit, a set of country, a set of city, a set of person who attend this meeting, a set of number, and etc. Okay. Now, the first, how to serve the set. We have some way, some procedure to serve the set. The first with enumeration. Each member of the association is registered in detail. For example, the set of the first 4 natural number we symbol by A. The member of A is 1, 2, 3, 4, and the set of the first 5 positive even numbers we symbol by B, B, the member of B, 4, 6, 8, 10, and random set, we symbol by C. For example, C, the member of C is it, A, Amir, 10, umbrella, and etc. And then R, A, B, A, B, C set in a set, and then a C, A, C set of a C, A, C in a set. Okay. In Melayu, we can call himpunan di dalam himpunan, ya. Okay. And etc. Okay. Now we discuss about membership. For example, this is the symbol mean a member. So we read this statement. Okay, is a member of a set. X is a member of a set. The opposite, X is not a member of a set. Example 1.2. Consider A 1, 2, 3, 4 and R, A, B, set of ABC, set of AC. K is a empty set or null set. So 3 is a member A because 3 is in ABC is member of R because ABC here is member of R. Okay, and then C is not member of R because C itself not provide in R. Yeah, in this R there is not C. Okay, so C is not a member of a set. And then null set, a member of K. Okay, this is null set in a K. And then null set is not member of R. There is not null set in R. Okay, I mean, I hope clear. And the next example, we have 3 sets. The first P1, the member of P1 is AB, the member of P2 is a set with a B, and the member of P3 double set AB. Now, so A member of P1 because A here is in of P1, and then A is not member of P2. In P2, there is not A itself. A with B, so A itself is not member of P2. P1 a member of P2 because all of P1 AB become member in P2 AB and etc. Okay, okay, you can learn more outside this session. I will share our presentation to the committee. Okay. This is basic symbols. We have P the set of positive integer, 1, 2, 3,
Indon
and
ni.
etc. Hello?
Universitas Airlangga, Indon. Ya.
Not clear? Tak tampak? Sorry.
Nampak, Doctor. I hope that the student can switch off your mic, please.
Okay. Okay, I will continue. Okay, N the set of natural number, Z the set of integer, Q the set of rational number, R the set of real number, and C the set of complex numbers. The universal set or the universe related to present a population in statistics symbol by S, or sometimes we symbol with U. U or S is not it doesn't matter, it's same in this case. Notation to from a set. Notation X where condition that must be met by X. X where condition that must be met by X. Example 1.4. A is the set of positive integer less than 5. So the member of A is 1, 2, 3, and 4 because less than 5. Or we can perform with another way. In this case, A, the member of A is X, where X is the set of positive integer less than 5. Or we can perform with A, the member of A is X, where X is element of P, or the member of P, when X less than 5. Okay. We can perform a set in Venn diagram. For example, consider S. S is same with U. Is it? It is universe. Universe. The universe member of the universe member is 1, 2 until 8, and A. The member of A is 1, 2, 3, 5. And B is a set with the member 2, 5, 6, 8. How to perform this set into Venn diagram? The performance in a Venn diagram is performed in this slide. So outside the circle is S or U, and then this is A and this is B. A include 1, 2, 3, 5. B 2, 5, 6, 8. 2 and 5 become member A and become member B. So 2 and 5 is an intersection in Venn diagram. Okay, the theory about intersection we'll discuss in the next slide. Okay. For 7, okay, we go to the next session about cardinality. Okay. Cardinality, the number of elements in a set called by cardinal from a set with notation NA or absolute A. It doesn't matter you want to use NA or you want to use absolute A. It it is same. Okay, maybe we go to the next example. We have B. B is a set where X the member of B, where X is a prime number less than 20. So we can mention B with 2, 3, 5, 7, 11, and etc. until 19. So the cardinality of B, or the number of elements of B, is 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, the second one, T is a set with a member of E is it, a cat, A, Amir, and umbrella. So the cardinality of T is 5, etc. And many more. We go to the next slide about null set or empty set. A set with cardinal equals to 0, called by null set. The notation of null set is like this or like this. Okay. The example, we have E. E is a set with X, where X is less than X. So is it impossible? It is impossible. So the cardinality of E is 0. Okay. And then P, Indonesian bulan in moon. Based on fact, there is no Indonesian people who have visit moon. So NP is 0. Okay. And the next, A, X, where X is square root from X squared plus 1 equal to 0. So NA is 0 because the square of X squared plus 1 is imaginary number. But as a remark, this is the null set in a null set is not the null set because it contains one element. What is the element? The element is the one and only is null set in this in this bracket. Okay. Okay. Now, okay. The next, we go to the next discussion about subset. Subset. We have A. A is a set, is said to be a subset of a set B if and only if every element of A is an element of B. In this case, B is subset A. So A subset B and B is subset by A. Okay. This is the notation of A subset B with the visualization in Venn diagram as follows. This is A and then A in B. Okay. Of course, A and B is the member of universe. Okay. Example 1.8. We have a set with member is 1, 2, and 3. 1, 2, and 3 is subset by 1, 2, 3, 4, 5 because 1, 2, 3 become a member in this set.
Dr. Fariz, sorry for interrupting. We cannot see your slide, Doctor.
Okay. Okay, wait for a minute.
Let's wait for a while. Again, I would like to remind students, please switch off your mic.
Okay, I'm so sorry because the our signal is bad. Okay. I will share again. Okay, tampak? Itu tampak?
Okey, Doktor, boleh nampak.
Okay. Okay, okay. Okay. I will repeat again with a subset. A set A is said to be a subset of set B if and only if every element of A is an element of B. So this is I perform A is subset B and B is subset by A. Okay, this is the Venn diagram. A in B with requirement A and B become the member of universe or U. Okay. The example, we have a set with the member is 1, 2, and 3. 1, 2, and 3 is a subset with 1, 2, 3, 4, 5 because 1, 2, 3 is in the this set. Okay. And then this is N subset Z, Z subset R, R subset C. What is N? What is Z? What is R and C? You can see in this slide. Okay. About basic symbol. Okay. N, Z, R, and Q. A subset B different with A proper subset with B. A in this notation, A is subset B, but A is not equal with B. So we can call A is proper subset by B. A is proper subset by B. For example, 1 and 2, 3 is proper subset from 1, 2, 3. 1, 2, 3 in this slide is a partition of 1, 2, and 3 of this set. Okay. The second one, A subset B, we can call A is subset B and A is equal with B. For example, we have A is 1, 3, and 2, and we have another set 2, 3, 1 is subset from 1, 2, 3. Okay. This is the difference between proper subset and subset. We go to the next slide. Okay. Next slide, we discuss about disjoint set. A set and B set. Okay, we have two sets, A and B. Will disjoin when both of them doesn't have at least a same element. Okay. Different element. Notation for this is the symbol. Okay. In this probability theory, disjoint set the presence of independent event. Independent event. For example, A is a man set or boy set. B is lady set or girl set. So A and B is disjoint. Okay. Okay, maybe A is regulation in Indonesia. B is regulation in Malaysia. Okay. Okay, so the regulation in Indonesia and Malaysia is disjoint because Indonesia and Malaysia have its freedom. Okay. For example, we go to example 1.9. A is set with X, where X element P, X less than 8, and B 10, 20, 30. So A disjoint with B. So when I perform in a line number, this is A, 1, 2 until 8 until 7. Okay, A, and this is B, 10, 20, etc. So A and B is disjoint set. Okay. Okay, we go to the next discussion about set.
Dr. Fariz, sorry.
Yes. Okay.
The slide doesn't appear again.
Okay.
Alright.
Okay, wait a minute. Kok gangguan terus ya? Okay.
Yeah, it's okay now.
Okay.
Alright.
Okay. Our slide is clear about set operation. Clear? Hello? My voice is clear?
Yeah, okay, Doctor. We can hear you.
Okay. Set operation. The first operation is about intersection. The notation A intersection with B. It means that X where X a member of A and X a member of B. In Venn diagram, you can draw a Venn diagram and perform with this Venn diagram. This is a basic Venn diagram about intersection. Okay. So this is in the middle of circle. This is A interaction with B. Okay. For example, if A 2, 4, 6, 8, 10, and B 4, 10, 14, 18, when A intersection with B is 4 and 5 a member of A, 4 and 10 is become a member of B. The next, if A 3, 5, 9 and B negative 2 and 6, then A intersection with B is a null X, a member of A, or X become the member of B. Okay. This is the representation in Venn diagram. So all of region in two circle, okay, become the area or become the member of A union B. We go to the next example. When A 2, 5, 8 and B 2, 5 and 22, then A union with B, okay, you can list the member of all of the member of A and all of the member of B. So A union B is 2, 5, 7, 8 and 22. So the second example, when A union by null set, so the result is A, or A union with universe, so the result is universe. Okay, we go to the third operation about complement. Okay. The notation like this, or sometimes some book noted by A complement like that. Okay, A complement means X, where X member of universe and X not member by a set. Okay. For example, in the Venn diagram, you can perform. This is the outside of the circle. The outside of the circle is this is a complement because in the circle is A. The outside is a complement or the complement of A. Okay. For example, consider S. S is same with universe. Okay, the member of S or universe is 1, 2, 3 until 9. If A equals with 1, 3, 7, 9, and A complement 2, 4, 6, 8, the member of S, but is not in a set. Okay, yeah, this is the complement. Okay, the second one, A, the member of A is X, where the fractional of X and 2 become member of B when X less than 9. Then the complement of A is 1, 3, 5, 7, and 9. Okay. Okay. Okay, I will go to the next slide. Tampak? Okay. We go to the next example. Okay. This is the for operator difference with the definition is as follow. A different B equivalent with A intersection with the complement of B. The example, if A 1, 2, 3 until 10 and B 2, 4, 6, 8 and 10, then A difference B 1, 3, 5, 7, 9. Okay, 1, 3, 5, 7, 9. Because okay, is same with A intersection by B complement. Okay. The member of A intersection with the complement of B is 1, 3, 5, 7, 9. It is different with B difference A. B different A is null set. Okay. You can use the definition to answer this example. Okay. And then symmetric difference. Okay. This is the notation. Symmetric difference equivalent with A union B difference with A intersection with B, or equivalent with A different B union B different A. This is the region of symmetric difference. Okay. This is the region of symmetric difference. Example, if A 2, 4, 6 and B 2, 3, 5, so symmetric difference between A and B is 3, 4, 5, 6. Okay, you can combine A union B. Okay, A union B is 2, 3, 4, 5, 6. And different with A intersection by B. Okay, A intersection by B 2. Okay. So the answer is 3, 4, 5, and 6. Okay. The sixth about Cartesian product, with the notation is A cross B. Okay, A cross B. This is A element A, or the member of A, and B the element of B. Okay, I will make shorten because the time is limited. Because after we go to set theory, we go to we discussion about basic concept about probability theory. Okay. This is the example. For example, A is a food set: steak, fried rice, nasi lemak, and noodle. B, beverage set: coffee, tea, drinking water. Okay, how many food and drink combination can the two set above? So we can answer the number of combination is about 12, because the member of A, they are 4, and the member of B, 3. 4 multiple with 3, the answer is 12. And we can list the members: stick with cola, stick with tea, stick with drinking water, and etc. This is the answer. Okay. Okay, maybe this is an speaking because the time is limited, so I will go to the next topic about counting technique. Okay, counting technique is a basic of probability. Counting technique include permutation and combination theory. Before we study about permutation and combination, we go to about multiplication rule and addition rule. Okay, this is the an illustration about permutation. Okay, consider a set for sub-object. Suppose we want to fill the position with object selected from the above four. Then the number of possible order arrangement is 24, and there the combination is A, B, C, B, A, C, C, A, B, and etc. Okay, the member of set is A, B, C, D. We arrange with 3 positions. So C, DAC, and etc. And you can see in this slide. So home arrangement can perform about this example. The number of possible order arrangement is 24. 24. Okay. 24. 24 okay. In clear? Okay. I will continue. The problem is we arrange for object. We want to fill 3 positions with object selected from for the member of set A, B, C, D. Okay. How to make all of two positions can be filled from the remaining 3 objects. The second position can be filled in 3 ways. The third position can be filled in 2 ways. And then the last position in only 1 way. So all of possibility can perform with 4 multiplied by 3 multiplied by 2 multiplied by 1. So the answer is 24. In general, if R positions are to be filled from an object, then the total number of possible ways they can be filled are given by n permutation with R. N permutation R represents the number of ways R position can be filled from an object. N permutation R equal with factorial of n divided by factorial of n difference with R. Okay. The factorial of n, same with n, multiple with n minus 1 or n different 1, multiple n difference 2, and etc. Okay, this is the illustration. How many different can the balls be placed in the box? Okay, we have 3 balls, red balls and blue balls white ball, and we place into different box 1, box 2, and box 3. So this is the combination. So box 1 red, the possibility box 2 B, or box 2 filled by white, and box 3 is the other color. Okay, this is all of the combination. So how many combination or how many way to place different order can the balls be placed in the box? The answer is 3 factorial. Factorial of 3 is 6. Okay. 1, 2, 3, 4, 5, 6. Okay. Definition. Each of the n permutation by R arrangement is called a permutation of an object taken R at a time. Okay. Example, how many permutation are there of all three of letter A, B, and C? Okay. There are 3 letters and we place by 3. So the answer is 3 permutation by 3. Okay. 3 permutation by 3 3 different 3 factorial. So the answer is 6. Okay. This example similar with our illustration about 3 ball and 3 box. Okay. The next example, find the number of permutation of n distinct object. So the answer is n permutation by n. Okay. 4 names are drawn from the 24 members of a club for the office at president, vice president, treasurer, and secretary. 24 members is select with 4 position or 4 arrangement. So the answer is 24 permutation with 4. Okay. Okay, we go to combination. In permutation, unordered is important. Okay. Unordered is important in permutation. But in many problems, the order of selection is not important and interest center only on the set of our object. Okay. Let's see, denote the number of subset of size R that can be selected from n different object. The R object in its set can be ordered in R permutation by R. Thus, we have n permutation by R is equal with combination between R permutation R. Okay. From this, we get this notation. Okay. This notation, and this is our concept of combination. So n combination by R is equal with the factorial of n divided by the factorial of n difference with R multiple with the factorial of R. Okay, this is combination theorem. Each of the n combination by R an ordered subset is called a combination of an object is taken R at time. Example, how many committee of 2 chemists and 1 physics can be formed from 4 chemists and 3 physics? So the answer, there are 4 chemists for chemic is taken to, okay, to chemic. So for combination 2, multiple with 3 physics taken from 1 physics, 3 combination 1. Okay. So using this concept, using this theorem, we can solve for combination 2 is 6, 3 combination 1 is 3. 6 multiple by 3, the equal is 18. Thus, 18 different committee can be formed. Okay. Other example, there are n balls that are not entirely different colors. So there are several balls that are the same color or indistinguishable. How many ways to arrange n balls into the box? Each box maximum consists of one ball or a ball. If we consider all the n balls to be different, then the number of ways to arrange the n balls into n box you can perform by n permutation by n or equal with the factorial of n. Okay. This is from an arrangement of n ball. There are n1 factorial to insert color ball 1. There are n2 factorial to insert the color balls 2 and etc. until nk factorial to insert colors balls k. Okay. This is the name of permutation of n element or permutation from an element. The notation permutation, we have n object and we arrange based on k element n1 n2 until nk. So the notation is permutation n divided by the all of selected element, okay, n1 factorial, n2 factorial, and until nk factorial. Or you can perform by n factorial or the factorial of n divided by n1 factorial, n2 factorial, and etc. Okay. For example, how many words can be formed using the letter of the word Mississippi? Okay. The word M, only one, I, 4, S, 4, P, 2. So the N is 11 letter in the Mississippi words. So the answer is okay. Using this formula, okay, this formula, the answer is 11 factorial divide 1 factorial and etc. The answer is this number. Or you can, the second way, you use a sum string using combination. So 11 letter taken 1 and then 10 taken 4 and etc. using combination concept. The equal is same. Okay, this is binomial theorem. Binomial theorem is important, for example, in binomial distribution, because in statistical analysis there are some distribution like one of them is binomial distribution, and binomial theorem is powerful to determine the coefficient of polynomial in mathematics. Yeah, okay, I will pass this theorem. Okay, maybe we go to the third subsection about probability measure. We introduce you about sample space. A sample space of a random experiment is the collection of all possible outcomes, while each element or the outcome of the sample space is called sample point. Okay. Example, describe the sample space of rolling a die and its sample point. So, as 1, 2, 3, 4, 5, 6. Because in a die, there are 6 sides, 1 until 6. S is the sample space. There are 6 sample points that shows the possibility of the number of the dice roll. Okay. The second definition, if the sample space consists countable number, you can count 1, 2, 3, and etc. Countable number sample points, then it is a countable sample space. And the third definition, if the sample space consists uncountable, okay, you cannot count because this is infinity. Okay. If the sample space consists uncountable numbers sample point, then it is continuous sample space. Okay. Countable sample space is a basic concept of discrete distribution in statistical method. For example, binomial, Poisson, geometric, and etc. And uncountable number space point is basic concept in continuous distribution. There are normal distribution and then chi-square distribution and exponential distribution and etc. Okay. Example. Okay, we pass the example. Okay, this is basic concept of probability. Let S be the sample space, okay, of random experiment. Okay, probability is always related of sample random. Okay, random experiment. A probability measure P is a set function with assigned real number to the various event of S satisfies probability of A is even, okay, is greater than 0 for all of even A member of F. F is field. Probability of S or universe always 1. Probability of null set, okay, null set or something is not possible is 0. Okay. Probability of union A set, a K consists of A1, A2, and etc. is same with or equal with the sum of probability AK. Okay, the summation start in K equal 1 until infinity. Satisfy the definition only if A1, A2, A3 until AK are mutually disjoint even of S that occur at the same time or not simultaneously. Okay. This is other theorem. Okay, maybe this is the theorem similar with the C point in this slide. Okay, similar. Let A1, A2, AN be a finite collection of n events such AE interaction by AG is null set or null for I is not equal with J. Then the probability of union AE, okay, consists of A1 until AN, same with the summation of probability AE. Okay, the theorem 3.2 I think is similar. Okay, maybe we go to the exercise. My student will help you to explain the exercise. Okay. Okay. Novel. Okay.
Hello, everyone.
Okay.
Can my voice be heard by all of the audience?
Clear. Clear.
Yes, very clear. I can hear you.
I think I cannot see Dr. Faris. Oh, yes, I can see now. Okay, maybe thank you for the chance that has given to me, Dr. Faris. Good morning, everyone. At this time, I would explain the exercise. Maybe this is a little exercise that I will give from all the lecture that has given from Dr. Faris, but after this, there are still some lecture that will be explained by Dr. Faris. So the first one is a die is loaded in such a way that the probability of the face with J dots turning up is proportional to J. So it's actually we have a dice or a die that we have the probability of we know die, right? It's about that a cube, a mini cube. We have dots that number 1 until 6. And what is the probability of one roll of the die that an odd number of dots will turn up? But there is a little note in here because the probabilities of dice number is not uniformly distributed. What it means not uniformly distributed? It means that every numbers that 1, 2, 3 inside the die is not have a does not have a probabilities like we know oftenly 1/6, right? Because there is summaries that the probability of the face with J dots turning up is proportional to J. Well, let J is the even of any number that shows up, like maybe the probability of that shows 1, 2, 3, it's equal to K times J, while K is proportional to J, right? Nah, by using the definition before, because the probability of all universe or maybe all of the sample space is equal 1. Then we have, really? Hello, is my voice clear?
Yeah, very clear. We can hear you.
Okay, thank you, doctor. Okay, I will continue my explanation. The probability of all the universe is actually the summation of all the events. That means the probability of number 1 is shown up, probability of number 2 is shown up, and etc. until the number of 6 is equal to 1. So, because the probability is proportional to K, we input the probability. First, if we want to look up about the probability numbers that is equal to 1, so we change the G with 1.
The slide suddenly disappear. Okay, please
Oh,
share
really,
the
doctor? Okay, I'm sorry for the inconvenience.
Okay, it's back now.
Okay, I will continue my explanation. So if we want to look up for the probabilities of the number that turning up is 1, it's actually k times 1. Then 2 means that k times 2, and then 3k times 3. If we sum all of that, we will have 21k, right? Now, because the probability of all universe is 1, that means 21k is equal to 1. So we have the k is 1 over 21. Because we have k is equal to 1 over 21, we have the probabilities of even that any number that shows up is actually equal 1 over 21 times j. So we back to the question. The question is only needed that the odd number of dots will turn up. How many odd numbers? There are 3, yeah? There is 1, 3, and 5. So it's based on the definition or the theorem that if we have the j is independent while I not equals to j, it means if we want to look the probability, we could always do the summation. So the probability of odd numbers that shows up is the probability that number 1 is shown up, number 3 is shown up, and number 5 is shown up. So it's 1 over 21 plus 3 over 21 and plus 5 over 21. We have 7 over 21. It's actually 1 per third. Okay, clear for the exercise number 1. So I will continue for the exercise number 2. This one is a little bit complicated because let S be countable sample space. Let OI, it means the element of OI from O1, O2 until the many of the sample, yeah, be the collection of all the elementary events in S. What should be the value of the constant C, such as the probability of events O is equal to C times 1 over 3 with the power of I, will be a probability measure in S. Using the definition 3.4 and theorem 3.2, we have the probability of all universe again is equal to 1. So if we want to look for the constant C, we need to do the summation for all of the probabilities, right? So the probabilities O1, O2, and so on. We have C times 1 over 3 plus 1 over 3 powers 2, and so on, so on. It's equal to 1. Nah, if we, maybe this is not under my explanation, but if if audience remember, we have the theorem of infinite summation in sequence theory. If the A or the numbers that from range 0 from 1, we actually could simplify the sequence into A over 1 minus the sequence itself. The sequence itself, it means if we look at the 1 over 3 plus 1 over 3 power 2, 1 over 3 power 3, and so on, it means that in the next sequence, the 1 over 3 is multiplied by himself. So if we apply in the sequence theory, so we have 1 over 3 over 1 minus 1 over 3, and it equals a half or 1 over 2. Since C times 1 over 2 is equal 1, so we have C is 2. Clear? Yeah, maybe that is some of the exercise.
Okay,
For the
thank you.
next, the explanation will be explained by Dr. Fariz again.
Okay, thank you, Kate. Okay, we continue for discussion about some property of the probability measure. This segment will show some theorem that will illustrate the various intuitive properties of a probability. Okay. The first theorem is it is similar with the theorem of complement of a set. If A be any event of the sample space S, then probability of complement A equals with 1, difference with probability of A. This is the Venn diagram. And then the second, if A and B are way 2 events, then probability of A union B is equal with probability A sum with probability B difference with probability A intersection with B. If A and B are disjoint event, then probability A intersection by B equals with probability of null set or 0. So probability A union B only probability A, okay, add with probability B because probability A union A intersection by B is 0. So probability A union with B, probability A add with probability B when A and B are disjoint event. Okay, we go to the next theorem. If A1, A2 until AN is a sequence of event in sample space S such that A1 subset of A2 subset until AN, then probability of AN is equal limit n go to infinity from probability AN. Okay, this theorem 4.4 is same, is about intersection between sum of events. Okay. Theorem 4.5. Okay. If A and B are 2 events such that A becomes subset of B, then probability B okay, with condition A equal with probability B difference with probability A. Okay, we go to exercise 4.1. Okay, maybe exercise point 4.1. Okay, my student Noval.
Okay, thank you, Dr. Fariz. I will share my presentation. Okay, can you see my slide?
Yes.
Yeah, very
Okay.
clear.
Okay, thank you. So the solve of exercise 4.1, the let A and B be events in a sample space S such that probability of condition A is a half, with it the same to for probability of the P, and probability of A complement intersection by B complement is 1/3. Find probability of A union B complement. Okay, the answer is notice that for the set theorem, if A union B complement is equal to A complement intersection by B complement. Hence, the probability A union B complement for the theorem of the disjoint event, P probability of A union B is same to probability A plus probability B. Now, is equal to probability A plus probability A complement intersection B complement. So the probability is a half plus 1 power 2 is the equal 546. Okay, we next to the exercise 4.2. A pair of dice consisting of a 6-side die and 4-side die are rolled, and the sum is determined. Let A be the event that sum 1.5 is sum of 5 is rolled, and B the event that a sum of 5 or 9 is rolled. Find probability A, probability B, and probability A intersection B. First, we define A and B sample space. Uh, A is element that sum of 5. This is 4 elements or sample points for sample space A, and the B is 6 elements or sample points. We can see that slide. Notice that A proper subset B, D probability of A intersection B is equal to probability of A. Then S will be have 24 elements. So probability A is 4 power 24 and probability B is 6 power 24 and probability A intersection by B is 4 power 24. Okay, thank you, Dr. Faris.
Okay, we go to the next topic about conditional probability. We begin with definition 5.1. Consider a random experiment whose sample space is X. We begin with definition 5.1. Consider a random experiment whose sample space is we are only concerned with use outcome that are element of B. This means that in many situations, we are only concerned with those outcomes that are element of B. This means that we consider B to be our new sample space. For the time being, suppose S is a non-empty finite sample space and B is a non-empty subset of S. Given this new discrete sample space B, discrete means related with countable number, how do we define the probability of an event A? Intuitively, one should define the probability of A with respect to the new sample space B. Okay, sorry. Our PPT is, I will share. Okay, that's it.
Okay.
Okay, sorry. Okay, we repeat again with definition 5.1. We go to conditional probability. Consider a random experiment whose sample space is S. Let B a subset of S. in many situations, we are only concerned with those outcomes that are element of B. This means that we consider B to be our new sample space. For the time being, suppose S is a non-empty finite sample space and B is a non-empty subset of S. Given this new discrete sample space B, discrete sample related with countable events, how do we define the probability of an event A? Intuitively, one should define the probability of A with respect to the new sample space B as see the figure. Okay, see that figure. P A given B, okay, the definition, probability of A given B equal with the number of elements in A intersection with B divided by the number of elements in B. Okay, so we can make in symbol, in mathematics symbol, probability A given B A equal probability A intersection B divided by probability B. Similar from P probability B given A equal with P A intersection with B divide probability A. Okay, this is our formula. We denote the conditional probability of A given the new sample space B as probability A given B. Hence, with notation, we say that probability A given B equal with the number of event in A intersection by B divided by the number of event B, or probability A intersection with B divided by probability B. Since the number of S or universe not equal 0 here, the number of S denotes the number of elements in S. Thus, if the sample space is finite, then the above definition of the probability of an event A, given that the event B has occurred, makes sense intuitively. Now, we define the conditional probability for any sample space. You can define with discrete or continuous sample space as follows. Okay, definition 5.3. Let S be a sample space that associates with a random experiment. The conditional probability of an event A given the event be greater than 0 or less than 1, because probability interval minimum 0, maximum 1. Okay. This conditional probability measure probability A given B satisfies all three axioms of a probability measure. That is, probability A given B is greater than 0 for all event A. Probability B given B, same with probability of universe or probability of sample space, PS is equal with 1. And then if A1, A2 until AK are mutually exclusive event, then probability of union AK given B same with the summation, okay, sum between probability AK given B. Okay, start from 1, 2 until infinity. Okay, example 5.1. A drawer contains 4 black, okay, 6 brown, and 8 olive socks. 2 socks are selected at random from the drawer. The first question, what is the probability that both socks are of the same color? And B, what is the probability that both socks are olive if it is known that they are of the same color? Okay. We try answer with define the sample space. So when there are questions about probability, you must define sample space and sample point. The sample space of this experiment consists of S, X, comma Y, okay, X, comma Y, the element of X, comma Y is black, olive, and brown socks. Okay. The cardinality of S is 18, 4 plus 6 plus 8, 18, and subtracted 2. So the answer 18 combination by 2. So the answer is 153. Okay. Next step. Okay, next step. Let A be the event that 2 socks selected at random are of the same color. Then the cardinality of A is given by NA for combination 2 for black, taken 2 for combination 2 plus 6 olive, taken 2, 6 combination 2 and 8 brown. Oh, sorry. Okay, 6 brown and 8 olive. Okay, 6 brown taken 2 plus 8 olive taken 2. Okay, we apply combination concept. So the answer 6 plus by 15 plus by 28. So the answer 49. Okay, therefore the probability of A is given by probability A. A is probability that both socks are of the same color. Okay, 49. Okay, 49 and A, or the cardinality of A, divided by their 18 socks taken by 2. Okay, so divide by 18 combination 2. The answer 45 divided by 153. Okay. Now we define new event B. B, the event that 2 socks selected at random are olive. Right. The color only olive. Then the cardinality of B is given by NB. They are at olive taken 2. So NB, or the cardinality of B, is 8 combination with 2. And and B divided by N universe. There are 18 shocks divided by 2. So 8 combination 2 divided by 18 combination 2. The answer is 28 divided by 153. Notice that B subset A hints. We go to definition conditional probability. Probability B given A equals with probability A intersection by B divided by probability A, or equal with probability B divided by probability A, because this is independent. So the answer is okay. Probability B 28 divided by 153, and probability A 49 divided by 153. So the answer is 4 divided by 7, okay, or 28 divided by 49. Okay. Okay. Maybe this is the illustration for conditional probability using a tree diagram. Okay, maybe we go to example 5.2. Okay, Tade or Novel? Novel, okay.
Okay, the example 5.2, the question is a pair of four side dice is rolled and the sum is determined. What is the probability that a sum of 3 is rolled before a sum of 5 is rolled in a sequence of rolls of the dice? Okay, now the answer of example 5.2, we define the sample space of this random experiment is, can you see the slide? Let A denote the event of getting a sum of 3 and B denote the event of getting a sum of 5. The probability that a sum of 3 is rolled before a sum of 5 is rolled can be thought of as the conditional probability of a sum of 3. Given that a sum of 3 or 5 has occurred, that is probability A with the condition A union B. Now with can you see the slide?
We can just now, but it just disappear. Can you share it again?
Oh, okay, thank you.
Okay, now we can see.
Okay. The probability A with the condition of A union B is equal to probability A intersection of A union B divided by probability A union B. It's equal probability of A divided by probability of A plus probability B, which the probability A is the cardinality of A divided by cardinality of A plus cardinality of B, which cardinality of A is 2 and the cardinality B is 4. So the probability A condition A union B is 1 divided by 3. Okay, we go to the Dr. Fariz presentation.
Okay, I will share my slide. Okay. We go to next definition. Okay. If an object is selected and then replaced before the next object is selected, this is known as sampling with replacement. Otherwise, it is called sampling without replacement. Rolling a die is equivalent to sampling with replacement, whereas dealing a deck of cards to player is sampling without replacement. Okay, for example, a box of fuse contains 20 fuse, of which 5 are defective. If 3 of the fuse are selected at random and removed from the box in succession without replacement, so the equation, what is the probability that all 3 fuses are defective? Okay, let A be the event that the first fuse is selected, the fuse selected is defect. The first fuse selected is defect. B, the event that the second fuse selected defect. C, the event that the third fuse selected is defect. The probability that all fuses selected are defect is probability A intersection by B intersection by C. Hence, probability A intersection B intersection C equal with probability A multiple with probability B given A multiple with probability C given A intersection B. So probability A 5 divided by 20 because there are 5 defects from 20 fuse. Okay, so this is 5 divide 20, and then 4 divide 19 because the fuse has taken one. So there are 4 fuse now, and the population is 20 minus 1, 19. So we take one again, one more. So probability say given A intersection by B is 3 divide B divide by 18. So the answer is 1 divide 140. Okay. Definition 5.5. Even A and B of a sample space S are called independent if and only if probability A intersection by B equals with probability A multiple with probability B. Okay, this is the example. Okay, the following diagram shows two events A and B in the sample space S. Are the events A and B independent? You can answer like using the illustration. There are 10 black dots in S, and event A contains 4 of these dots. So the probability of A is 4 divided by 10. Similarly, event B contains 5 black dots. Hence probability B 5 divided by 16. The conditional probability A given B, the equal is 2 divide 5. This shows that probability A given B equal with probability A. Hence, A and B are independent. Okay, this is our theorem. Okay, theorem 5.1. This is theorem 5.1. Let A be subset S if A and B are independent. Probability B greater 0. Probability A given B equal with probability A. And then the 5.2, if A and B are independent even, then complement of A and B are independent. Similarly, A and B complement or complement of B independent. Okay. Okay, I pass the proof. You can learn outside this session. Okay, this is theorem 5.3 and 5.4 related independency and mutually exclusive. Okay. 5. The concept of independence is fundamental. In fact, it is this concept that justifies the mathematical development of probability as a separate discipline from measure theory. Okay, Marquez said independent of event is not a purely mathematical concept. It can, however, be made plausible that it should be interpreted by the rule of multiplication of probability, and this lead to the mathematical definition of independent. Okay. Okay, this is excerpt 5.1 novel. Okay, time is yours. Sharing.
Okay, can you see my slide?
No, we couldn't. Have you shared it? Okay, we can
Okay,
see it.
thank you. Okay, the exercise 5.1. The question is an urn contains 3 red, 2 white, and 4 yellow balls. An order sample of size 3 is drawn from the urn. If the balls are drawn with replacement so that one outcome doesn't change the probability of others, then what is the probability of drawing a sample that has balls of each color? Also, find the probability of drawing a sample that has 2 yellow balls and a red ball, or a red ball and 2 white balls. So, to find the probability of drawing a sample that has balls of each color, we need to calculate the probability of each color being selected at least once in the sample. Okay, the probability of selecting a red ball on each draw is 3 divided by 9. Since there are 3 red balls out of a total of 9 balls in the urn, since we drawing with replacement, the probability remains the same for each draw. Similarly, the probability of selecting a white ball on each draw is 2 divided by 9. And the probability of selecting a yellow ball on each draw is 4 divided by 9. Okay, to find the probability of drawing a sample that has balls of each color, we multiply this probability together since the events are independent. Uh, it's the probability red, white, and yellow. So the probability is red ball is the probability of white ball, and this probability of yellow balls is the result of the multiplied these three probabilities is 8 divided by 243. And for the probability of 2 yellow, 1 red, or 1 red and 2 white is multiplied the probability of 2 yellow and 1 red plus the probability of 1 red and 2 white. This result of the probability is 20 divided by 243. If the balls are drawn without replacement, then the probability of red, white, and yellow is 3 divided by 9 times 2 divided by 8 and times 4 divided by 7, which the result of 1 divided by 21. So the probability of 2 yellow, 1 red, or the probability 1 red, 2 white without replacement, the probability is 4 divided by 9 times 3 divided by 8 times 3 divided by 7 plus 3 divided by 9 times 2 divided by 8 and times 1 divided by 7. The result is 7 divided by 84. Okay, thank you, Dr. Faris. We next to the topic.
Okay. The last topic is about bias theorem. Nampak, nampak? Okay, we start with definition 6.1. This is the last topic. Nampak? Okay. Thank you. Let S be a set and let P consist of a set with the element of AE. E start from 1 until M, be a collection of subset of S. The collection P is called a partition of S. If S is equal with from 1, 2, 3 until M, and B, AE intersection and AG is 0, or AE, AG is independent each other for I not equal G. Okay, this is the partition of S, A1, A2 until A5, when S divide to 5A. Okay. Theorem 6.2, if the events constitute a partition of the sample space S and probability of Pi is not 0 for I 1, 2 until M, then for any event A in S, probability A equal with sum I equal 1 until M, probability Bi multiple with probability A given Bi. Okay, this is a proof. And the theorem 6.3, if the event constitute a partition of the sample space S and probability Bi is not 0 for I 1, 2 until M, then for any event A in sample space S such that probability A is not 0. So probability Bk given A is equal with this formula. Okay, K equal with 1, 2 until M. Okay, maybe we go to the exercise, maybe, Kadek. Okay, because the time is limited. Okay, Kadek.
Okay, can my voice be heard?
Clear.
Okay,
Yeah.
let me share the. Oh, it's already shared. But first of all, I need to claim something that my camera is not functioning at all. So I'm so sorry that I can.
It's okay.
Maybe aku share langsung aja. Tampak. Aku share langsung aja. Wait, let me reshare the PowerPoint. Is it already? Exercise number 6.1, 60% of new drivers have had driver education. During their first year, new drivers without driver education have probability 0.08, it's equal to 8% of having an accident. But new drivers with driver education have only 0.05 probability of an accident. What is the probability a new driver has had driver education, given that the driver had no accident the first year? So first of all, we need to understand the problem. What the question is asked is the probability of a new driver that had driver education with a conditional probability that the driver had no accident the first year. So we know that this driver had no accident at the first year. The answer is, first we need to represent every event that happened in the problems. Let A represent the new driver who has had driver education, yeah, and B represent the new driver who has had an accident in his first year. So A is only education, B is represent the accident. It means A complement and B complement is the opposite of A and B. A complement means that a new driver who has had not driver education. And B complement is the new driver who has had not an accident in his first year. So we want to find the probability that a new driver has had driver education. So it's A, but it's had no accident. It means the B complement. So we have the probability A with conditional B complement. We go to the basic. Probability A with the conditional that given B complement equals to probability A intersection B complement divided by probability of B complement itself. Now, for the probability, so we can rewrite the probability A of intersection B complement as probability B complement with conditional A times probability A. Why? Because if we rewrite the probability B complement with conditional A, yeah, it equals to probability of B complement intersection or join A over probability of A. Now, if want to look up or find the probability B complement intersection A, it means we can move the probability A to the left side. Then we have the first numerator or probability B complement with A conditional times probability A. While the probability B complement, we can use the theorem from the Bayes theorem. I mean the expansion. So the probability B complement equal to this. But we cannot just put the number of probability. We need more expansion. Probability B complement with conditional A, it could be rewrite as 1 minus probability B with conditional A. Over now, the probability B complement over A with conditional A, it could be rewrite as this. And also probability B complement with conditional A complement, it could be rewrite as this. Now we want to input the probability. If probability B complement over A means that the probability that the driver has had no accident, if we know that this driver have education, we go back to the question. %60 of new drivers maybe have had the driver education. So It's literally means 1 minus probability B with conditional A is the 60% of this driver that have education times the probability A, which the new drivers with education had only 0.05 of an accident. So we tried the no accident is 95 over 100 is 95% over we put the other numbers, yeah, 40, and the probability A it's I'm sorry, the probability A it's actually this, right? Yeah, 0.08. So if we want to find the have not accident, it's equal to 92%, right? So it's 40% times 92% plus this would be 60% and times the complement of A itself, yeah, it's equal to probability A complement. It's equal to 95%. Then we have this 0.6. It's around about 60%, yeah, 60%, 0.77%. Okay. Now the last example, it's a little bit complicated, yeah. 1/2% of the population has AIDS. There is a test to detect AIDS. A positive test result is supposed to mean that you have AIDS, but the test is not perfect. For people with AIDS, the test misses the diagnosis 2% of the times. And for the people without AIDS, the test incorrectly tells 3% of them that they have AIDS. What is the probability that a person picked at random will test positive? And B, what is the probability that you have AIDS given that your test comes back positive? So this is only a single probability and the B number is a conditional probability, right? Now, let A denote the event of one who has AIDS and let B denote the test comes out positive. The probability that a person picked at random will test positive is given by probability test positive. What theorem we should use in this section? We go back to Bayesian theorem, this one, yeah. It's actually this theorem, yeah. Let me scroll up, and up. Yeah. And which one, eh? I think, this one. So if you want to look up for the single probability, it's actually the summation of the probability of the second event times probability of the event itself, but given the conditional of the second probability, the second event. Okay, wait, let me, because the theorem is long, yeah, maybe I need to note that one. Wait a second, yeah. Oh no. Is my voice can be heard?
Yeah.
Okay, I will continue my explanation. So if we want to look at the probability test positive, we need to find the probability. So probability of B yeah is equal the summation probabilities of A, yeah, maybe AI. I'm sorry for the bad notes. times the probability of B, or it outside the probability with conditional, I'm sorry, probability, let me just clear this note. Times of the probability of B with conditional AI. So we have, if we go back to the question, 0.5% of the population has AIDS. There is a test for people with AIDS. The test misses the diagnosis 2% of the times, and for the people without AIDS, the test incorrectly tells 3%. Yeah, of them that they have AIDS. So the probability of the event of one who has AIDS, it would be the 0.005, right? Times the probability of the B given to AI1, it could be 0.98 plus the probability of A2, right? 0.995 times 0.03. It equals to 0.035. It equals to 3.5%. So we have the probability of B itself, of B, or the event that comes out positive is 0.035. We also could look at the tree diagram. We have the probability of AIDS, probability no AIDS, and from this AIDS, it comes to possibility. Is the test will be positive or the test will be negative? The same one goes for no AIDS. There are two possibilities. The test is positive or it will be test negative. This tree diagram will help us to answer the B point. The probability that you have AIDS given that your test comes back positive is given by. So probability A with conditional B, it's equal favorable positive branches. Now, if we look up for the basic, it equals to A probability of B. But if we look at the Bayes theorem again from this one is actually probability, yeah, probability B, okay, B times probability of kebalik. Bener kok. Probability of A, ya. So we have the number is the probability of age 0.005 and the probability that comes out as positive. It means this one is probability B with conditional A and this one is probability A, right? So it times 0.005 times 0.98 over the total positive branches. At the exercise 6.1 again. So if we total all of the branches, it means 0.005 with these terms, yeah, the first terms, plus the second terms. What is the second terms? The second terms is actually the complement from the first term, right? So it's actually 0.995 we have this from 1 minus 0.005. And 0.03 we have from, it's the complement of this, yeah, not a complement, I'm sorry, but the complement is this, yeah, this one. So the probability B that given complement A with no H, right? So it equals to 0.14 or 14%. Yeah, that's the final answer.
Okay, thank you. That's for the last exercise. For the last remark. Okay, as a remark, this example of the last exercise illustrates why Bayes' theorem is so important. What we would really like to know now in this situation is a first test result. Do you have AIDS? But we cannot get this information without an autopay. The first state is hidden, but the second state is not hidden. The best we can do is make a prediction about the first state. This illustrates why backward conditional probability are so useful. Okay, I mean this is enough for our session because we have learned about set until Bayes theorem. Okay, so we conclude that the probability concept is very important to all of major, all of study. And this is only the beginning of probability. After that, we must learn about the distribution of probability and further theorem about probability. Thank you for your attention, and I'm sorry if there are some inconvenience, especially about the network. Our network is trouble. Okay, thank you. I will go back to the moderator. Okay, thank you.
All right. Can you hear me?
Okay.
Very well. Okay. All right. Thank you so much to Dr. Faris, and also we have the two assistants there, Mr. Naufa and also Mr. Kadi. Thank you so much for your explanation. We hope that our students are able to get the sharing knowledge and will be able to answer well for this topic in their final exam later. And before we end our session, we are going to take a picture of all the participants together with Dr. Faris and the assistant. So I hope that our student can switch on the camera first, like give them a few seconds to switch on the camera, right? And Dr. Liana is there to take a picture. This is for the record. And Dr. Liana, are you ready?
Yes, yes.
All right. So, yeah. Okay, participant. We have a quite a number of participants. We have almost 240 just now, but I think because of the time frame, we almost the whole over Jumaat time, so they might have some other matters. Okay, we are sorry for that, doctor, because some already left a bit early. But then let's wait for a while. Okay, Dr. Liana, you ready?
Okay. Wait. Just give me a moment, please.
Right. Dr. Faris, these two students are doing bachelor with you, degree, S2,
Yes,
S1?
bachelor degree, S1, S1.
Oh, S1. Major in statistics?
Yes, bachelor in statistics. Both of them have visited Malaysia together with me.
Oh, I see. I look at your background. You're from mathematics before you do S2 in statistics, right?
Yes. Okay.
Excuse me, Dr. Fariz. Could you
Okay,
please
Doctor.
stop sharing the slide, please? Please,
Oh, it's
your
not
slide.
sharing.
Alright.
Okay.
Still sharing?
Alright,
I will
student.
stop share. I have stop share.
Yeah.
Alright.
Okay.
If there is no more to switch on the camera, so I would like to take the photo now. Okay. Alright. So say, are we still waiting for the student, or we can take now?
We can just proceed then.
Alright. Okay. Alright. Okay. So everyone smile. 1, 2, 3. Okay. One more. 1. Wait a minute. I face first. I face first. All right. Okay. Another one. 1, 2, 3. Smile, everyone. Okay. Thank you.
Together more.
Okay, thank you, Doctor. We wait you to come in Indonesia.
Inshallah.
Right.
I will see you again.
Inshallah.
Thank you so much, Dr. Faris.
Thank you, Dr. Faris and students. Thank you. Assalamualaikum.
Assalamualaikum.
Waalaikumsalam.